Hello, hello. Welcome back to another episode of this shit. Today we're going to be doing Vesper Theory. Vesper Theory, Lewis structures are two-dimensional representations of three-dimensional structures. However, we generally need to know the shapes of these molecules or whatever because it determines important properties um, later on. So we can use a theory known as valence shell electron pair repulsion theory, or Vesper theory, to predict these shapes. Um, For those of you that are so mathematically inclined, you can actually use a bit of vector calculus to derive both the bond angles and the bond angles and yeah, mainly the bond angles, and yeah, you can essentially use that to determine the overall shape, because what you essentially want to do here is you would maximize the distance between two vectors to minimize the electrostatic repulsion between them, and that would correspond to a specific angle with respect to, I think it's cosine theta. You would minimize your dot product or something. You would involve math on that sort. Anyways, I'm getting a little bit out of hand. So what we so firstly, I would like to define a few terms. An electron domain is a region of space around an atom occupied by either a lone pair or a bonded atom. For the higher levels out there, I think this alternate definition would make much better sense. It's either a lone pair or a sigma bond. But we'll get to that in the higher level section. What is a sigma bond? What's a pi bond? All that stuff. The total number of electron domains can be calculated for a given atom of interest in a molecule by this little formula here: number of lone pairs plus number of atoms bonded. Electron domain geometry is the spatial arrangement of electron domains. Um, yeah, the spatial arrangement of electron domains is what we call the electron domain geometry, and then the molecular geometry refers to the shape of a molecule. So the positioning of atoms, um, the spatial arrangement of atoms within a molecule is what we call the molecular geometry. Um, Molecular geometry is dependent on the number of lone pairs in the central atom and the atoms bonded to it, and the number of atoms bonded to it, I should say. Um, these are a bunch of shapes that you're expected to know. Um, what I recommend is memorize. So the way you put two electron domains in space is the maximum angle is 180 degrees and it's linear. It looks like a line, and that makes perfect sense to us, right? If you want to put if two electrons put to minimize the repulsion between two electrons, we put them on opposite ends, right? That makes sense. So therefore, that makes sense. And then for three electron domains, we have something which is known as trigonal planar, which the bond angles are 120 degrees, and it sort of looks like a triangle. Which that also makes intuitive sense, because if you place three electrons around a proton, they would generally tend to form a triangle. So as you can see here, doot doot doot. There's your triangle, and they're 120 degrees away from each other. The only non-intuitive one initially is the tetrahedron, but again, remember, we consider 3D space, and in 3D space, the way to maximize the distance between four vertices is by a tetrahedral arrangement of them. The higher levels have to know two others, but we're going to get to that when we get to that. So there are some rules for drawing geometry diagrams. We use this wedge and dash notation here, as we can see. The wedge indicates it's in front of you, whereas the dash indicates it's behind you. So it's hard to do in 3D space, but I'll try. I'll draw here. I'll only focus on one example just for the sake of time. So here, let's pick. I think if we did CH4, that's a good example. So CH H H H. So that's sort of what methane would look like as a molecule. I'm doing my best here to try and represent this in 3D. However, with the formalism attached to it. I wonder if I can select freeform. Oh, that does work. Right. However, with the wedge and dash notation, we would draw a C here, H, H, and then we would draw a triangle there, and then immediately right beside it, we would do a dash. So the wedge indicates it's in front of you, and then the dash indicates it's behind. That's not too bad, actually. And then for lone pairs, we do this followed by a little bubble around it just to indicate that that's there when we do geometry diagrams. So I'm not going to do any more because it's going to waste precious time. I might do a video worksheet later at some point. So yeah, a bond angle is the angle between two bonds, so that's pretty obvious. An angle between a bond and a lone pair is an angle, but it's not necessarily a bond angle. So in a linear molecule, it's 180. In a trigonal planar molecule, it's 120. And in a perfectly tetrahedron, it's 109.5. However, this can vary slightly just due to the size of, a few things. One, just the size of the atom. Bigger atoms will cause bigger repulsion. And then two, lone pairs tend to take up a lot of space, and therefore they cause more repulsion than just atoms as a whole, since I don't know why, but they just do. So as a result, they kind of push in on the atoms a little bit. So for example, in ammonia, this lone pair causes these bond angles to be about 107 degrees. The two lone pairs on oxygen cause that to be about 104 degrees, and so on and so forth. And one of the reasons we're really interested in shape is because we can use it to determine molecular polarity, if something is polar or not. And this is really important because it'll indicate what sort of properties the substance would have at a macroscopic level. Now, how do you determine polarity? Well, it's quite simple, I guess, but for the sake of going over the process, I'm going to do a couple of worked examples. So let's take this one, CH2Br2. Firstly, you can skip a few steps, but I'm going to go through it as, formally as possible. What I'll do is I'll draw this, CH, H, that's a terrible wedge. Then we're going to do the dash. I'm not going to draw on the lone pairs on the bromine, just too much work. And then the way I like to do it is I like to treat them like vectors. So carbon has a higher electronegativity, so the bond, the dipole moment would go like that. And then similarly it would go like that. Just remember that those are equal. And then because bromine is more electronegative than carbon, it's going to go like that, and then like that. Now, what do we get if we pull these vectors together? So we get that, we get that, and we get that, and we get that. And then what is the net vector sum of those vectors? Now, you're going to have to take a bit of a guess, but I would be willing to say it's something along the lines of, there's your net dipole. So I'm going to go ahead and take that as a guess. I'm going to go on a limb here and say that that's it. But as you can clearly see, these vectors here, if we put that tail to tip, it would something like that. And if we put those vectors here tail to tip, it would result in something similar. And the result, the net dipole, is that. And therefore, that molecule is polar. Because we can clearly see here, there's a positive charge and accumulation of positive charge. And here's an accumulation of negative charge. So that's sort of roughly how you're meant to do it. It does take a bit of time, and I'll probably do a video worksheet dedicated to this sort of thing. But for now, that's sort of how you do it. So, have I missed anything? No, I don't think so. So yeah, with that, thank you for watching. Don't forget to like and subscribe.